All right, so up to now, scientists knew that electrons had characteristics of waves and as well as characteristics of particles, but their theories did not provide a complete description of the electronic behavior. Well, that was resolved in 1926 by Austrian physicist Erwin Schrödinger, and he used a really complicated mathematical technique which described the behavior and energies of submicroscopic particles. In general, an equation that was analogous to Newton's laws of motion for macroscopic objects. So Schrödinger's equation requires advanced calculus to solve, and we're not going to deal with that. I'm just going to gloss over the main parts. What's important to note is that his equation incorporated both particle behavior in terms of mass, right, mass m, and wave behavior in terms of what he called a wave function, all right? And the symbol that we use for that is psi. That's that little wavy thing right there. But it's psi, psi, which depends on the location in space of the system, such as an electron in an atom. Okay, so the wave function itself really has no direct physical meaning, but the probability of finding an electron in a certain region of space is proportional to the square of that wave function squared. Think about it. That idea of relating psi squared to the probability stemmed from the wave theory analogy. According to wave theory, the intensity of light is proportional to the square of the amplitude of the wave. Think about what that says. The intensity of light is proportional to the square of the amplitude. Remember what amplitude is? Amplitude is from the zero line to the peak. So the place where it's most intense is where the amplitude is squared. That makes sense. So he took that and he applied it to the probability of finding an electron. So the most likely place to find an electron is where psi squared is the greatest. All right, don't get too nervous about all of this. I know this seems very foreign, but this, again, is just a background information. We're going to be dealing with quantum numbers, and for you to understand quantum numbers, you should understand the quantum mechanical descriptions and where that comes from. All right, so I want to recap what's most important about Schrödinger's equation. Number one, the equation specifies possible energy states that the electron can occupy and identifies the corresponding wave functions. These energy states and functions are characterized by a set of quantum numbers that help us construct the model of the atom. That's the most important. We're going to learn the 4 different quantum numbers, all right? But these energy states are defined by Schrödinger's equation. That's why this is so important. Although quantum mechanics cannot pinpoint an electron in an atom, it does define the region where the electron might be at a given time. That was the whole point for the psi squared and the electron density. It gives us where the electron density is the highest at a particular moment. So electron density gives the probability that an electron will be found in a certain area. And we'll see that the highest density is usually towards the nucleus of an atom. When we say that an electron, we're going to start talking about orbitals very soon. And when I say that an electron is in a certain orbital, we mean that the distribution of the electron density or probability of finding that electron in the orbital is really high. Because again, we don't really know where they are. We can just give probabilities because of the densities that we see. In quantum mechanics, there's 4 quantum numbers, but 3 are required to describe the distribution of electrons in atoms. Think of quantum numbers like an address. Okay, so for you to find your friend, you need his or her address. So that's what it is. Quantum numbers give the address, basically, of where you would most likely find an electron. All right, so the first of the 4 that we're going to learn is called the principal quantum number, and it has a symbol n. This one's the simplest one, okay? So this one determines the energy of the orbital, and it tells you how far you are from the nucleus. The principal quantum number basically gives you the average distance of the electron from the nucleus. So the larger n is, the greater the average distance of an electron in that orbital from the nucleus. So now is when it's really important for you guys to be able to read your periodic table. So for example, hydrogen would be 1s. So as you go down the rows, it would be 1s, and then lithium would be 2s, and then sodium would be 3s, so on and so forth. The principal quantum number depends on nothing else. It's the principal one. And the reason I say that is because L, M sub L, and M sub S do depend on the quantum number right before it. So again, principal quantum number depends on nobody and basically just tells you how far on average that electron is from the nucleus. And the number is given to you by what row it sits in the periodic table. All right, let's move on. The second quantum number, we have a symbol of L. It's called the angular momentum quantum number. This one basically tells you the shape of the orbitals. I'm going to go ahead and just explain to you all four quantum numbers, and then I'm going to show you different shapes, and things will start to make sense a little bit more when we get there. But for now, let's just stay with me. So L, we've got angular momentum. Now, L depends on what N is. Okay, so for a given value of N, remember that's the principal quantum number, that's the row that it's in, L will be from 0 to N minus 1. For example, if my N is 1, then L can only be 0. If my N is equal to 2, my angular momentum can only be 0 or 1. If my N, the row that it's in is 3, the principal quantum number is 3, then L can only be 0, 1, or 2. If my N is 56, my L can be 0 up to 55. Okay, so that's, obviously that does not exist, but I just wanted to give you an example. So for a given value of N, your L will be 0 up to N minus 1. Now, L equals 0 represents the s orbital. And this does not make sense to you right now, but the s orbital basically only has one shape. That's why it can only have a 0. L corresponding to 1 is a p orbital. The p orbital can have 3 different shapes, and you'll see what I mean by that later. L equals 2 is the d orbital, and that can have 5 different types of shapes. Remember, all these things are in 3D, and I will show you shapes so you understand that better. But the most important thing here to remember is angular momentum L depends on the principal quantum number, and for you to find out the number of L, you've got to give it from 0 to N minus 1. And again, this tells you the shape of the volume of space that the electron occupies. Let's move on. The third quantum number, M sub L, is called the magnetic quantum number. This guy tells you the orientation of the orbitals. Remember, all these things are in 3D, so they all have different orientations. This number indicates the number of orbitals inside a subshell. That doesn't make any sense to you, but it will. Okay, so let's go back. Principal quantum number N depends on nobody. Angular momentum quantum number L depends on N, the principal quantum number. M sub L, the magnetic quantum number, depends on L. So the way that you find this one is for a given value of L, M sub L will be negative L to plus L. Okay, so what does that mean? So if I have an angular momentum of 1, then my magnetic quantum number will be from negative 1 all the way to the positive 1, going through 0. If my L is equal to 2, then my M sub L has to be negative 2, negative 1, 0, 1, 2. If my L is equal to 0, then M sub L is 0. Basically, this one tells you the orientation of the orbital in space, and I've given you how to find what the actual values of the magnetic quantum number are. Let's go to the last one. The last one is the easiest one. You don't really even have to remember much. The last quantum number is the spin. Here we have to assume that electrons act like little tiny magnets. And basically what we think is that they spin on their own axes, just like Earth does. So according to the electromagnetic theory, a spinning charge generates a magnetic field. And it's this motion that causes the electrons to behave like a magnet. M sub S does not depend on anybody either. All you have to know is that when you pair electrons up in an orbital, one has to be spin up and one has to be spin down. So one has to be plus 1/2 and the other one has to be minus 1/2. Again, I understand these things are not going to really make sense to you just yet. We're going to do problems and you'll see how this is really not hard at all. Things we've learned so far is we have 4 quantum numbers. The first one is the principal quantum number. That tells you how far you are from the nucleus. It depends on nobody. The second one is the angular momentum quantum number. That gives you the shape of the orbital, and that depends on n. L depends on n. The third one is the magnetic quantum number, m sub L, and that gives you the orientation of the orbital. And that one depends on what L is. And then you have m sub S, which one is plus 1/2 and the other one is minus 1/2. All right, so this is basically how the periodic table is broken up. So for example, let's say I have hydrogen. Hydrogen would be the first one on the left, which is 1s. Okay, so the 1 refers to how far you are from the nucleus, and the S is basically the shape, which is that L, the angular momentum quantum number. So how many electrons does hydrogen have? It has 1, so you would say 1s1. If we went to helium, helium is also in the same row, right? So it has the same principal quantum number, and it also has the same shape because it's still an S, but it has 2 electrons, so you would say 1s2. Now we go to lithium, for example. Lithium is right under hydrogen, and you would say, okay, so now it's in the second row, so we have to say 2s. How many electrons does lithium have? Well, it has 3. So if I wanted to write the electron configuration for lithium, I would say 1s2 because I have to go through everybody else to get to lithium. Okay, so I have to go through hydrogen and helium. So I would put 1s2 and then I would put 2s1, and that's a total of 3 electrons. And we go on like this through all of the different elements. We're going to practice this a lot, so don't worry. But I want to show you some other things before we actually do some problems. Alright, so this shows a plot of electron density in the hydrogen 1s orbital as a function of the distance from the nucleus. Notice that the electron density falls really rapidly as the distance from the nucleus increases. In the second picture, they've basically put a boundary, right? They've just drawn like a circle, boundary surface diagram of the hydrogen 1s orbital. In this picture here is really a more realistic way of viewing the electron density distribution. And the way they do it is just by dividing the 1s orbital into successive spherical thin shells. And then the last picture I have is a plot of the probability of finding the electron in each shell, which is called radial probability, as a function of the distance from the nucleus. And you can see that it's a lot more probable to find an electron near the nucleus, because it's a lot more dense, than if you were to look for one in the last shell right over here. Alright, that's all I want to talk about for this video. We're going to really go into details, and I'm going to show you some nice pictures of all the different types of shapes and everything. So everything's going to start to come together in the next video. But we're going to resume with section 7.7, which deals with atomic orbitals.